So this BoF is really to make people aware of a project that's still in its early stages. We haven't really got anything to talk about.
Isn't that contrary to the nature of a BoF? How can you be
well, I'm expecting there's a lot of, because once I explain what it's about, I think there'll be a lot of input about where to research, because if I explain what the problem is, then a lot of people will have the answer, I expect. So this is all about information leakage. And in particular, the idea that if you build a secure system, it can leak information in all sorts of ways. And probably the best known one is differential power analysis, where by measuring the power consumed by a chip, you can work out what the program's doing. And this is a 4-year project funded by the Engineering and Physical Sciences Research Council in the UK at Bristol University. So it's a pure academic research project. And amongst, it's looking at how you can improve tooling to make systems more robust against information leakage. Okay? And one of the tools, but only one of the tools, it addresses EDA tools and so forth, is the compiler part of it. And indeed, there's a full-time postdoc available, and there's a vacancy there. What prompted me to make this talk was a desperate email from Elizabeth Oswald saying it's 9 months in, we still have not found the postdoc to do the compiler work. It's an academic research project, but Embecosm is what I think is referred to as an industrial sponsor, which means we wrote to EPSRC saying this is really important academic research. As a company, we fully support it. And in order for that to look real, what we've committed to is that we will take the postdoc in every summer for a 3-month internship. And our role will be to take that research and put it into GCC and LLVM. Quite a lot of the ideas, as will become clear, are not new, but they don't appear in standard. No one's actually put them into commercial compilers. They've put them into PhD compilers. Okay. So let's have a look at what we're talking about here. There we are. So this is the sort of thing we're looking at. Mostly it's not about getting the compiler to magically make your code secure. It's getting it to help you. So the sort of thing that we want to watch about, differential power analysis works best if you have critical variable, something like a cryptographic key that is controlling the flow through a program, because then the amount of power used will be varied by which way the key goes. And people have demonstrated that you can extract cryptographic keys by measuring the power, and that's quite old. That's 10 or 15 years old. But it can be done by instruction timings, so how fast does my program run? It can be done by looking at memory access, how hot does my flash get? And one way to solve that would be to put an attribute on a variable saying this is a critical variable, and have the compiler flag up a warning saying this variable is being used to control a loop. More interestingly, an alias of this variable is being used to control a loop. A good security programmer probably won't put a critical variable controlling a loop, but they may inadvertently have an alias doing the same thing. So that's one that direct compiler stuff, that's been known about for years, but no one's ever put it into GCC or LLVM, so we wanted to get that put in there. Another one we've implemented for a particular customer as proof of concept, but not made general yet, is simple things about not leaving stuff lying around in memory. Now, this is not directly information leakage, but it's certainly an attack surface that looking for variables lying around. So when you return from a function, either clear the stack frame, set the stack frame, some random value. Same with long jump, do the same thing. Okay, I've interrupted, so this is a BoF, so if I missed anything. Another one, which is a hard one, and we've got this one with a real customer at the moment. Sometimes you duplicate operations in code. So you say A equals 37, do a bit of code, and then say A equals 37 again. And the compiler immediately throws it out. But the reason for doing that, or even A equals 37, do some stuff, if A is not equal to 37, blow up. And the compiler will eliminate that because it's a third constant. And the reason is one form of attack is to use intense radiation on a chip to cause it to do spurious bit flipping. And critical stuff, you make sure it really hasn't changed And the problem with the compiler is it will throw that stuff away. So we have customers who are compiling with all optimization disabled in what is generally performance critical code.
But isn't that a case where they should have been using a volatile?
Sometimes you can use a volatile, sometimes, I think that one's a trivially obvious one, you can use a volatile. There are more complex examples where a volatile doesn't work, where you don't just want a variable assignment, you want a block of code or something.
And what's the solution to that? You annotate the code saying...
You annotate the code, some way we want to find, and this is, it's the beginning of the project, so we don't quite know how to do it, but how can you annotate the code in a way that says, this may seem obviously throwawayable, but you cannot throw this stuff away, it's got to stay. That needs more exploring, and indeed...
How would the programmer know where to put those annotations?
So these people are generally, so these are crypto guys, they're specialist crypto guys, they generally know where they think their code is bad. So this is an example where and we get examples from our customers, they say, look, here's our program, your compiler's thrown it all away. And we say, yes, it has, it's doing nothing. They say, no, it's meant to do nothing. It's meant to be there. And the volatile example is one example. One of the problems with volatile is that it is volatile everywhere. And I may only want this one particular place. I want this particular one preserved. So one of the comebacks was, this variable's used all over the place, and suddenly I've made it volatile, and you've had a big impact.
Could this problem be solved by area-specific optimization?
Yes. So one option is opt none, or attribute opt none. We've tried that. That does work in this particular case, but it was a big function, so it was an awful lot of opt none. And what we're trying to do is give a richer choice in that particular one. Now, there are some of these techniques which I'm still getting my head round. One is code shuffling. When you do scheduling of your code, you choose a particular ordering, but often there's some variability in the way that you actually order instructions. This instruction could go before that because they're completely independent. Code shuffling is quite good for making code not reliably go down the same route every time. The potential actually to say space may not be a problem, in which case I can have 3 different ways of doing this, and at random I'll do one of them, and they have the code shuffled in different orders to make it harder to work out what's going on. And there's quite a bit of work on that. There's this idea of atomicity, and I'm really struggling to get my head around this, which is basically that you try and balance all your control flow paths, so that whichever control flow path you go through, it looks the same, and you have uniform blocks, and you put them in different orders to do things. And I scratch my head and say, is it really possible to do anything useful while achieving this? And there seems to be some theoretical ideas out of inductive logic programming that says you really can do this. The idea here, certainly that we've had on our preliminary discussions, is not that the compiler would do this, but the compiler may take input from some supporting analysis to help it do that. There's always a balance between the compiler doing stuff and the compiler warning about stuff you've done. One that is quite important for cipher code is what's called bit slicing. And that's where you take a variable that may be 32 bits long, but you don't put it all in one 32-bit block in memory. You put a bit here, a bit there, a bit there, a bit there. And whenever you use it, you recombine it when you use it. Now, people go to a lot of careful lengths hand-writing this stuff using macros, and you can imagine with a big cryptographic key, that's awfully painful. But it's the sort of thing a compiler could do automatically for you. And in fact, one of the problems bit slicing sometimes hits is modern compilers are so good, they say, you're doing this bit, we can put them all back together into one big 32-bit thing for you, which is exactly what you don't want. So trying to do that is one that we're looking at. That'd be a question of an attribute on a variable that says bit slice this variable. You have to tie into the linker because you want the linker to put stuff in different places. One idea that is entirely speculative is whether super optimization, which optimizes against an arbitrary criterion, if you can actually measure leakage in some analytic way, can you actually super optimize to say this code sequence is the least leaky sequence I could generate? That's sort of got not much further than the hand waving, well, super optimizes against arbitrary criteria. How we actually tie that into metrics of information leakage is a bit difficult. Algorithmic choice, this is particularly low-level algorithms, that sometimes low-level algorithms, there's more than one way of, say, sign extending a number, and so forth. And again, in the hope of disrupting analysis, can you actually have a program use different ways, multiple different ways of doing the same algorithm? And indeed, that may tie into the super optimization, because the usual case with super optimization is that it comes up with a dozen candidate instruction sequences for a particular operation. Can you actually allow the program to use all of those just under different times? And the last one is one that is, does the compiler that's working on this sort of stuff have enough information? It can start to say, there's some common themes here. How do we extend the instruction set to minimize information leakage? Now, again, I think that's a bit in the hand-waving, sort of, we've got 4 years for this project, let's have a think about it stage. So those are the ones that, on our kick-off meeting, the academics bounced around. We do have real customers. I'm trying to think, have we missed anything out?
Well, if you're going to hardware before you if you're actually going into hardware before you extend the instruction set, you can make sure that the instructions you do have look more uniform with different data and also among each other.
Yeah. So part of this project which we're less involved with is that whole, I'll hold it, is that whole issue of the wider tool chain, and certainly some of our commercial compiler development, we work closely with the hardware guys who are simultaneously changing the instruction set under our feet to make it less leaky. And we have one case where actually the semantics of an instruction was changed at a very late stage, causing much of the compiler and libGCC, or it was actually LLVM this one, so compiler RT, to blow up. So yeah, that is a factor. We're focused on the compiler side of it. And really the purpose of flagging this up is, one, to make people aware of the general idea. Secondly, if there are ideas we're missing or things we haven't thought about, we'd love to hear about them and get them on tape.
Oh, can I just ask then, taking a step back, you mentioned that this is all about preventing leakage of information.
Yes.
And you mentioned power level monitoring as one method. But aren't there lots of other methods as well? And isn't this actually a much larger area that you need to look at?
The answer is yes, and I'm not a security and crypto guy, so I'm sort of a bit getting into exactly all the other different ways of attack. And indeed, some of the things I've mentioned are not even about information leakage. We're certainly, from a compiler perspective, actually putting it in the wider context of how can the compiler help you write more secure code. One of our sidelines that Simon and I are involved with is actually on the Internet of Things Security Foundation, which is mostly focused on the electronics side and pretty basic stuff, but we're driving the tools side of that a bit, as to, sometimes you can write insecure code because the tools really don't help you. So, no, I agree, it's much wider than just differential power analysis.
Have you considered introducing NOPs or non-useful instructions to obfuscate the code?
Absolutely, yes. NOPs, other instructions, I mean, it ties into this, several of these code shuffling, algorithmic choice, code balancing. Can you code balance execution time by inserting instructions that do nothing? And indeed, just not NOPs, but arbitrary instructions that are not going to break anything.
Yeah, we've looked at techniques. We've looked at techniques that you kind of extend that. So you say, well, we could introduce loads of junk operations into our program, but that bloats the code. So how about we'll generate the hardware will generate NOPs, or a bad case, because they generally get thrown away very early on. And then you end up at the stage where you say, well, actually, we'll just randomly stimulate logical blocks so that the multiplier maybe drives some junk data through. There's junk on the bus, we don't care, we're going to throw away the answer. But it's generating some leakage that's outside of the program flow, just to disguise the interesting stuff that's going through the machine. So certainly techniques like that exist.
Couldn't all of, well, it won't apply to other things, but couldn't a lot of this be handled at a hardware level by hiding power emissions? I mean, if you properly shield something, surely it can't be measured.
The answer is yes. I mean, whenever we deal with this with new chips, that's definitely the case. Sometimes this is a matter of working with what I've got already, and if the processor is out there, and we're trying to aid the person using a standard part. If you look at Internet of Things, which is, since we deal at the deeply embedded area, it tends to be where we worry about. If you're putting an AT Tiny or something, or an AT328, on Arduino scale thing in there, that's a 10-year-old part, and they're probably, Atmel probably aren't going to go and change the design because someone's come up with a whizzo way of reducing the power leakage. But if we can help you make it a bit less insecure, that's quite good. I think if you get down to the when you start to get down to people doing smart cards or serious, crypto security, and they're designing chips purposely for the case, we're really concerned with the recent example of the Osram light bulb that allows you, it's internet connected and you can hijack someone's home network through the light bulb. It's that sort of product which is not going to be using specialist hardware, but which we can at least make it really quite hard work to hijack someone's world. And we're only part of the story. I mean, we can make the code as secure as you like, but if you're actually going to offer an open peephole into someone's internal secure network, the best code in the world won't help you. Any other ideas, suggestions, comments?
The slicing is interesting because, certainly we've got I've seen applications where you put quite sophisticated hardware scramblers on the memory interfaces, which is trying to, again, tackle that from the hardware side of things. They're expensive and they cost you time and performance to do that. So having the ability to mark code to be automatically scrambled, essentially by the program knows how to scramble it. Assuming that your code base is fundamentally secured, which it nearly always is in these applications in some way. That's quite a cute idea, I think.
Yeah, I think probably we have similar objectives, which is we're working on the smaller end of the world, where some of these options are great if you've got buckets of memory. Some of them are not so great, and I think a lot of what we'll be doing is looking at, if you've got buckets of memory, you can do this. If you're pretty tight on memory, these are still improvements you can make. And this is an entirely open project, though we have customers obviously who are interested in this. This is being done in the open. It's explicitly open source, free and open source, with our agreement with Bristol University. So anyone and everyone's welcome to join in. And I finish off I think we're probably getting to the stage of winding up. I hope to come back next year and tell you about lots of good things. And if you do know of anyone who might be interested in that position at Bristol University, do spread the word around, because it'd be a shame if this didn't get off the ground because the academics couldn't find anyone to do the work. Okay? Thank you all very much.